Therapy delivery into the brain has been a big problem for decades. We felt that the solution needed a real thinking out of the box strategy. In many neurological disorders, we know what the treatment is. We know the protein that we can bring in that will reverse or at least alleviate the symptoms. The problem is bringing the protein into the brain. The blood-brain barrier and also the cell membranes of the cells of the brain, of the neurons, are barriers for these proteins. For the last several years, we've been studying the parasite that causes toxoplasmosis, which is called Toxoplasma Gondii. 33% of the world population is infected with toxoplasmosis. The symptoms are quite mild. Some people don't even know that they got infected. Our team, primarily Shahar Bracha, who is the student who kind of led the whole project, decided to use these parasites because they naturally cross the blood-brain barrier and go into brain cells. Because we're able to manipulate the parasite, modify it, we decided to make parasites that can produce the proteins that are therapeutic and therefore, through their natural route of infection, come into the brain cells, and then deliver those therapeutic proteins in the brain. So in that way, we're kind of trying to piggyback on the parasite to become a miniature courier, a micro courier, to bring in therapy into the brain. We're experimenting with different types of therapeutic proteins. In the long run, kind of down the road, this research could make a huge difference for cognitive disorders that affect millions of people. These disorders can only be partially treated at the moment. Some examples include Alzheimer and Rett Syndrome. Toxoplasma is still a pathogen. It can cause severe diseases, and it can even be fatal. This is, of course, in rare circumstances and very well-defined circumstances, but it's still a very important and serious risk. The Toxoplasma research community is still understanding how the parasite interacts with the immune system, how it interacts with the brain. There is a lot of skepticism around whether or not this is ever going to be a valid, proper therapeutic product. But also it's a very, very exciting opportunity that I think we should continue to explore. We have a great team of people who've been working on this. This has been a huge collaborative effort. There are collaborators in the US, in Switzerland, in Israel, in Italy, each one doing their own little part, but all together we have a real good proof of principle. And we are lucky to be supported by funders that made it happen. The Nadal Colton Applied Research Fund, rettsyndrome.org, and of course the University of Glasgow Knowledge Exchange Fund.